Hi, my name's Matt Willits, and this is a look at my ME575 project presentation. About the project itself and defining it, it was to design a controller to stabilize a system that had an actuator, a sensor, and a load. So in this case, our actuator would be the motor, our sensor would be the encoder built into the motor, and our load is the mass and the pendulum arm itself. So moving forward, I wanted to determine the dynamic forces on the system and then simulate and analyze the results. I decided to go with the generic problem included with the assignment. So you have a motor gear head assembly with a built-in encoder and a load M, and you are trying to maintain a reference angle in radians. Kind of reiterating it, the project description is creating a controller that stabilizes a motor-driven pendulum. So to do this, you have to create a dynamic representation, a state space representation, and then going further into the requirements of the assignment was analyzing the effects of different step sizes and different sinusoidal inputs. For this analysis, I decided to do a PD, a PFFC, and an LQR controller, and wanted to see which one would work best. For our forces acting on the system, there's three main torques. There's the torque from the motor, there's the resistance from the inertia of the pendulum, there's the weight of the pendulum itself. And so the values I used, so I used an inertia for the pendulum and motor of 0.02, a viscous damping coefficient of 0.02, pendulum mass of half a kilogram, and the distance or the length of the pendulum, I used 0.3 meters and used your standard gravity coefficient of 9.81 meters per second squared. For the dynamic equations, the goal of this was to simulate all of the torques about the system. So you have your torque from the pendulum inertia, your torque from the motor, and the torque from the weight of the pendulum. Rearranging this, and you get your input or the torque of the motor on the right. So that's U of t in this scenario. It was abridged for this presentation. And when you rearrange that even further and eventually do a Laplace transformation and factor everything out, you get your transfer function on the bottom of 1 over js squared plus bs plus mgl. And so this is the plant that is used by the PD controller. Controller design is looking for the reference angle, so it's your distance from your desired angle. So in this case, solving for E of t, where R of t is your goal angle and Y of t is your distance from it, or your active angle position. So using the generic form for a PD controller, we're able to solve for KP and KD. I actually ended up using MATLAB to solve for this, to find one that would get us within the required specs. Eventually, this results in our final transfer function in equation 30 that is set up and plugged into MATLAB to solve with Simulink. FC design is essentially the exact same thing, but you have a pre-pass filter. So that filter is shown in equation 31. To define the reference, it's put in the form in equation 32. So it's essentially doing the exact same thing as a PD, just with a filter to adjust it and adjust the overshoot, as well as the rise time and our necessary inputs. A little bit of a different route. Another option is to use an LQR controller. We went over this fairly late in 575, but I also took 577, so decided it would be a viable option, given what I've learned. So there's a couple different aspects to this, but it's essentially just trying to minimize the amount of equations that are needed, and some of this involves using the Riccati equation listed below. So all of these equations work together to create your state space matrices, which are then plugged into MATLAB or Simulink and used to solve. So this was another option that I explored and wanted to see how effective it would be for this kind of solution. So for our design requirements, there's quite a few that were decided upon. So for percent overshoot, this is also a lot of times symbolized as MP. I wanted less than 10% overshoot. I wanted a rise time of less than half a second, a settling time of less than or equal to 2 seconds, a steady state error less than 0.004 radians, a reference step input of 0.2 radians, and this is adjusted later to show the effect that adjusting the reference step has on the equation. And then an overshoot limit line for, in this case, 10% is 0.22 radians. So that's what was looked at for this analysis, but that was adjusted later. So this is kind of just going through the tuned gain values resulted in a KP of 20.7553, KD of 2.554. So using those values for both the PD and the PFFC, we received an overshoot on the PD of almost nearly 10% and went right up there, but the rise time was incredibly low. The settling time was also very, very low, but that overshoot once again was very high. The PFFC had a much lower overshoot, but had a far slower rise time, but still well below the target of half a second. And its settling time was also much longer at 0.325 seconds. Both of these had very, very low standard or steady state error to the point that they were almost unrecognizable. It wasn't even worth putting like it was well under the target goal. The LQR had 0 overshoot, so it went up and approached the goal but never went over. It had a rise time of 0.49 seconds, so almost went right up to that target line. And it had a settling time of 0.876 seconds. So all of these were well under the settling time requirement, and that could probably be lowered and adjusted. They also all had very, very low steady state error, so neither of those conditions were a problem for these systems. Here, a full plot can be seen, and it can be seen that they were all going up to that 0.2 radian angle goal. So you can see that the PD angle shot straight up and over and then settled back down, but it did not exceed the 10% overshoot. Comparatively, the PFFC went up quite a bit slower, barely went over, and then came back down. And the LQR controlled system did not go overshoot at all, rose slowly up to the line, stayed at the line, all within the required settling time. So this kind of shows that depending on your situation, if you want to rapidly reach your goal, the PD controller might be the better option. Somewhere in between would be the PFFC. And if your goal is just to come as close as possible to the goal with no overshoot, the LQR is going to be your best option. Sinusoidal analysis of the systems. So on the left was uh, very small. It was 0.05 hertz was what was used, and then in the middle was 1 hertz, and then on the right is 2 hertz. The main thing to be noted here is that once you surpassed 1 hertz, there was really little difference in the system and how it was affected. At that point, it was very minimal. Going with the very low frequency of 0.05 hertz on the left, your motor input almost exactly matches what you're putting in with that analysis. Um, Overall, it just depends on your goal and what you're looking for. Uh, but there wasn't significant changes based off what hertz was used as far as the response of the system and how it reacted. The goal step response was changed. So you have point 0.1 on the right, point 0.2 in the middle, and point 0.3, or point 0.1 on the left, point 0.2 in the middle, point 0.3 on the right. And all systems still behaved relatively similarly, with PD going for that rapid overshoot, then coming back down, PFFC relatively somewhere in the middle, and then the LQR gradually rising up. Despite the increased gap, they all still met the requirements, so it didn't result in a significant change in the system. So for a quick summary, all three controllers can stabilize the system. PD is good for rapid stabilization with larger overshoot. PFFC is more in the middle, so if you want to get there rapidly but with very minimal overshoot, and LQR will take significantly longer to get there but with 0 overshoot. So depending on what you're looking for, the controllers will all be effective. It just depends on how much overshoot you want and how well within your parameters you want to fit. So quickly, here's a list of references from the system. Uh, Nothing crazy here, just looking into PD control, PID control, and the necessary requirements. All of my MATLAB code is at the end of my report. I did not want to fit it on a slide. So if you have any questions, let me know. Thanks. Bye.